Today, we're going to have a review for Chapter 14, Partial Derivatives. First, what is a function of two variables? A function of two variables is a rule that assigns to each x, y in the xy plane a real number f of x, y. Think of that as the z-coordinate of this point. The graph of a function of two variables is a surface in 3D. Describe three methods for visualizing a function of two variables. One way to visualize a function of two variables is by graphing it. You see here, this surface is the graph for this function z equal to f of x, y. Another method is a contour map. We can set the function equal to different constant k, and then we can get the lower curve on the xy plane, and those lower curves are horizontal traces of the graph of the function projected onto the xy plane. A third method is to use an arrow diagram, such as this one. For each ordered pair x, y in the domain on the xy plane, we're going to assign a unique real number f of x, y on the z-axis. Number 2. What is a function of three variables? How can you visualize such a function? A function of three variables is a rule that assigns to each order triple x, y, z in the domain of the function a unique real number f of x, y, z. We are not able to graph a function of three variables as it will require 4 dimensionals. However, notice that a function of three variables is an extension of a function of two variables. For a function of two variables, we examine the lower curves. And now for function of three variables, we're going to examine that function by level surfaces. So for example, look at this picture over here. We have three level surfaces. The first one is f of xyz equals c1, and the other one equals c2, and one more equal to c3. We have three different level surfaces. Using those level surfaces, we can visualize function of three variables. What does the limit of this function f is equal to L as x, y approaching to a, b mean? And how can you show that such a limit does not exist? The limit of the function f of x, y as x, y approaching to a, b, that limit is equal to L means that the function is going to approach to the number L as the point x, y approach to the point a, b along any path that is within the domain of the function. So take a look at the graph over here. We have this function f of x, y. Notice that this function is not defined at 0, 0. And when x, y approaching to 0, 0, then the limit here is equal to 1, means that no matter how x, y approaching to 0, 0, think about like a fish swimming along the surface of this graph of this function. And as long as x, y is going to 0, 0, the fish can get arbitrarily close to this point here, where the z-coordinate will be 1. So along any path, this fish swimming toward that always get arbitrarily close to this point right there with the z-coordinate equal 1. Now, on the other hand, we have this function g. This function right there, that's the graph of the function. This is function g. The limit of this function as x comma y approaching to 0 comma 0 does not exist because if you approach to 0 comma 0 along different path, sometimes you get 1 right here, and sometimes you get, say, -1 over here. And as long as you can find two different paths that the limit are not equal, then you can conclude that the limit does not exist. What does it mean to say that function f is continuous at a comma b? A function f is continuous at a comma b means that if the limit of the function as x comma y approaching a comma b is equal to f of a comma b. In other words, that means you can do a direct substitution, substitute a and b into x and y. If function f is continuous on R2, what can you say about its graph? For example, this function f is continuous on R2, and you see that the graph is a surface without any holes or break. On the other hand, this function here has break here and also here. So the function that has this graph over here is not continuous on R2. Write expressions for the partial derivative with respect to x at a comma b and partial derivative with respect to y at a comma b as limits. The partial derivative of the function with respect to x at a comma b is given to be the limit of this quotient as h approaching to 0. Notice that when you take partial derivative with respect to x, the x component here will change from a to a plus h. Now, when we take partial derivative of the function with respect to y and evaluate at a comma b, that's equal to the limit of this quotient. Notice that the y component will change from b to b plus h. How do you interpret partial derivative with respect to x at a comma b and the partial derivative with respect to y at a comma b geometrically? We can interpret the partial derivative of the function at a comma b as the slope of the tangent. For example, this a comma b on the xy plane, then the partial derivative of the function with respect to x at a comma b will be the slope of the tangent line that's tangent to this curve C1 at this point P. C1 over here is the intersecting curve of this vertical plane, y equal to b, intersecting with the surface. That's the intersecting curve. And the pink one right there is the tangent line to C1 at this point P. The partial derivative with respect to x of the function f at a comma b is the slope of this tangent line that's tangent to this curve C1. The partial derivative with respect to y at a comma b will be the slope of this tangent line tangent to this curve C2 at the point a comma b, where C2 is the intersecting curve of this vertical plane with the surface. How do you interpret them as rates of change? If z is equal to f of x comma y, then we can interpret the possibility of the function with respect to x as the rate of change of z with respect to x. And in that case, we regard the y here as a constant, we regard the y here as fixed, and only the x here is changing. Similarly, the possibility with respect to y, we can interpret that as the rate of change of z with respect to y. And at this time, x here is regarded as a constant, and only the y here is changing. If the function f of x comma y is given by a formula, how do you calculate the possibility with respect to x and the possibility with respect to y? To find the possibility with respect to x, we're going to regard y as a constant and then differentiate the function with respect to x. Similarly, to find possibility with respect to y, we're going to regard x as a constant and then differentiate the function with respect to y. Here's one example. This function is equal to e to the xy times ln of z. Now, when we try to differentiate that with respect to x, we're going to regard y and z as a constant and regard x as the only changing variable. So ln of z here is a constant, and we can put that in front of e to the xy. So we have ln of z in front. And then multiply that by the possibility of e to the xy with respect to x. Now to do this, we need to use the chain rule. So exponential function, the duality here, that will be e to the xy. And by the chain rule, multiply with the possibility of this inner function, xy, with respect to x. Now, because y here is regarded as a constant, now the possibility of xy with respect to x will be y. So the result will be y times e to the xy times ln of z. What does Clairaut's theorem say? Clairaut's theorem says that if f is a function of two variables that is defined on a disk that containing the point a comma b, and the second possibility of the function first with respect to x and then with respect to y, and the possibility first with respect to y and then with respect to x, they are both continuous on D, then Clairaut's theorem states that the two second possibility will be equal at a comma b. In other words, the order that you take possibility here doesn't matter. How do you usually verify that the function f is differentiable? If the possibility with respect to x and with respect to y exists near a comma b and are continuous on a comma b, then we say the function f is differentiable at a comma b. State the chain rule for the case where z is a function of x and y are functions of one variable. And what if x and y are functions of two variables? So here we have z as a function of x and y, and x and y are functions of t. To find the derivative z with respect to t, we will go along all the path. So that will be partial derivative with respect to x times dx dt plus partial derivative of the function f with respect to y times dy dt. Now, z here is a function of x and y are a function of two variables, s and t. Then the partial derivative of z with respect to s will be partial derivative of z with respect to x times partial derivative x with respect to s. And then if you go along the other path, then we need to add partial derivative of z with respect to y times partial derivative y with respect to s. So we can use the tree diagram to help us to remember the chain rule. Similarly, we can get the partial derivative z with respect to t by looking at the two paths to go from z to t. If z is defined implicitly as a function of x and y by an equation of this form f of xyz equal to 0, how do you find partial derivative of z with respect to x and partial derivative of z with respect to y? If the big F function is differentiable and the partial derivative of that with respect to z is not 0, then we can find the partial derivative of z with respect to x and also with respect to y by these two equations. Notice that the denominator over here is not 0, and you see the x and this x here match, and the z and z here match. And for this partial derivative, you will see the y and this y over here match, and then the z and z over here match. Both of them on the right hand side as a negative sign. For more details of this, you can refer to the note on implicit differentiation in section 14.5, the chain rule. Write an expression as a limit for the directional derivative of f at x0, y0 in the direction of a unit vector u equal to the vector a comma b. How do you interpret it as a rate? And how do you interpret it geometrically? The directional derivative of the function at x0, y0 in the direction of a unit vector u equal to a comma b is given by the limit of this difference quotient. Notice that the a and b here, those are the component of this vector, this unit vector u. Here's a page of recap from our note in directional derivative. We can think about the directional derivative in different way. Think about that as rate of change of the function in the direction of this unit vector u, and we can also think about that as the slope of the tangent line t to this intersecting curve c at this point p. Geometrically, we can think about the directional derivative here as the rate of change of the function. Say z here is the function of x and y. We can think about the directional derivative as the rate of change of z in the direction of this unit vector u. And we can also think about that as the slope of this tangent line t to this intersecting curve c here at this point p. If f is differentiable, write an expression for the directional duality of f in the direction of u at the point x0, y0 in terms of the partial duality of the function with respect to x and the partial duality of the function with respect to y. The directional duality of the function in the u direction at this point x0, y0 is given to be the partial duality of the function with respect to x at x0, y0 times a plus the partial duality of the function with respect to y at x0, y0 and then times b. Notice that a and b are the component of that unit vector u. Define the gradient vector for a function f of 2 or 3 variables. If the function f is a function of 2 variables, then the gradient vector will consist of 2 components. The first component will be the partial duality with respect to x. The second component will be the partial duality with respect to y. The gradient vector for the function f of 3 variables will be defined similarly. Express the directional duality of the function f in the direction of the unit vector u in terms of the gradient of f. The directional duality of the function f in the direction of u is given as the dot product of the gradient of f dotted with the unit vector u. Explain the geometric significance of the gradient. The gradient vector of a function gives the direction of maximum rate of increase of the function. Here, this big F is a function of 3 variables. The gradient here points in the direction of steepest ascent, and it is perpendicular to the level surface of the function. Over here, the function f is a function of 2 variables x and y. The gradient points in the direction of steepest ascent, and the gradient vector is perpendicular to the lower curve. What do the following statements mean? What does it mean the function f has a local maximum at a, b? The function has a local maximum at a, b if the function value at a, b is greater than or equal to all the function value f of x, y, where x, y is near this a, b. In other words, f of a, b is going to be the maximum value for all those point x, y that is near a, b. So locally, it is a maximum. The function f has an absolute maximum at a, b. That means that f of a, b is going to be greater than or equal to all other function value in the domain of the function. Notice that this time is in the whole domain of the function. So this is the absolute maximum in the whole domain of the function. The function f has a local mean or an absolute mean at a, b are defined similarly. What does it mean that f has a saddle point at a, b? F has a saddle point at a, b if f of a, b is the local maximum in one direction, but a local minimum in another direction. If f has a local maximum at a, b, what can you say about its partial derivative at a, b? If f has a local maximum at a, b, and the function has the first partial derivative exists over there, then the partial derivative with respect to x and the partial derivative with respect to y will both equal to 0 at a, b. In other words, the gradient of the function will be equal to 0 at a, b. What is a critical point of the function f? A critical point of a function f is a point such that the partial derivative will be equal to 0 over there, or one of those partial derivative does not exist. State the second derivative test. Suppose the second partial derivative of the function continues on a disk with the center a, b, and suppose that the partial derivative at a, b will all equal to 0, which means that a, b is a critical point of the function. And we're going to let d to be defined this way. The d here is equal to the determinant of this matrix, which is fxx times fyy minus the square of fxy. Now, when d is positive, we're going to compare that with fxx. If fxx is positive, then the function value will be local mean. If fxx is negative, then the function value will be a local max. Now, when d is negative, then the function value is neither a local max nor a local mean. In fact, at a, b, that point is a saddle point. What is a closed set in R2? What is a bounded set? A closed set in R2 will be those sets that include every point on its boundary, like this too. Every point in the boundary is included. Now, if we omit some point on the boundary, say there's even only one point is omitted on the boundary, then the set is not closed. What is a bounded set? A bounded set is one that is contained within some disk. For example, this set here, we can find a disk to contain that set. No matter how big the set is, if we can find a disk to contain that, then that set is a bounded set. In other words, the set is finite in extent. Say the extreme value field for functions of two variables. If a function f is continuous on a closed and bounded set, like this d over here, then guarantee that the function f is going to attain an absolute max and an absolute mean inside this closed bounded set. Say if the function attains an absolute max f of x1, y1 and an absolute mean f of x2, y2 on this closed bounded set D, those max and mean are called extreme values. They can occur in the interior of this closed bounded set or at the boundary of this closed bounded set. How do you find the values that the extreme value field guarantees? To find the extreme value that we stated above, we're going to first find the critical points of the function inside the set D. We can find those critical points by setting the partial duality all equal to 0. Those critical points will be in the interior of this set D. Say we found 3 critical points inside the interior of D. And then we're going to find the extreme values of the function on the boundary of this D. Because the extreme value can only happen either at critical points or at the boundary of the set. So we're going to compare the function value at those critical points and also the extreme values on the boundary of the set. Then the largest of those values will be the absolute max, and the smallest of those values will be the absolute mean. Explain how the method of Lagrange multipliers works in finding the extreme values of f of xyz subject to the constraint g of xyz equal to k. What if there's a second constraint? To find the maximum and minimum value of the function subject to this constraint over here, we assume that those extreme value exist and the gradient of g does not equal 0 on the surface of that graph of this equation. We will first find all values xyz such that it satisfies this equation. The gradient of f is lambda times the gradient of g. In other words, that gradient f and gradient g are parallel vector and also satisfy this constraint equation. So we try to find x, y, and z that satisfy these two equations, and we got those x, y, z. After we got those x, y, z, we're going to evaluate the function value at those x, y, z, and then we're going to compare those function value. The largest of those values is the maximum of f, and the smallest is the minimum value of f. If there is a second constraint, h of xyz equals c, then we just need to add one more Lagrange multiplier, mu, times the gradient of h of xyz. Notice that lambda and mu, those are Lagrange multipliers.